Hello everyone, Victor is here, your organic chemistry tutor, and today I want to talk about organic solvents. So when it comes to organic solvents, we can generally break them into two different categories. Those are going to be non-polar solvents, and non-polar solvents, they lack a permanent dipole, so that means that they are overall uniform in their electron density, and that means that they do not have a more or less electron-rich or electron-poor part of the molecule, making them completely neutral in that sense. Examples of typical nonpolar solvents are going to be compounds like hexane or other alkanes, or for instance you might see CCl4, which is a very nonpolar compound. However, due to the environmental impact of this solvent, we typically try not to use it nowadays. Another somewhat common nonpolar solvent is going to be benzene, which is an amazing solvent. However, due to the environmental impact and also the toxicity of benzene, we also tend to not use that solvent very often either. Another important category of solvents is polar solvents, and unlike nonpolar solvents, polar solvents, they do have a permanent dipole, which means that one part of the molecule is going to be permanently more electron-rich than the other part of the molecule, making the molecule into a little bit of a dipole. So on one end we are going to have a positive charge, and on the other end we are going to have negative charge in the molecule, or partial positive and a negative. So sometimes you can see that we represent those with delta plus and delta minus signs like that. A classic example of a polar solvent is going to be something like water, H2O. If we look at water and think about its structure, we have an oxygen atom which is connected to two hydrogen atoms, like so. An oxygen atom also has a couple of electron pairs, so from the electron density perspective, we have two electron clouds over here. We have a partially positive charge on our hydrogens. Due to the difference in the electronegativities, oxygen is going to pull electron density towards itself, making hydrogens positively charged, partially positively charged I should say, and that creates an overall dipole in the molecule oriented like this. Other examples of polar solvents are going to be molecules like, let's say, dichloromethane or DCM, or you might encounter THF, tetrahydrofuran, or you can see CH3OH or methanol, or we might even see acetic acid used as a polar Protic solvent. But here is the thing. Not all polar solvents are the same. We are going to separate our polar solvents into two different categories on their own as well. Those are going to be polar Protic solvents and polar aprotic solvents. It is sometimes a little bit confusing when we pronounce one versus the other one, so I will try to emphasize A in my aprotic solvent as much as I can whenever I'm talking about those different types of solvents. So let's talk a little bit more about those solvents and what they're all about. So first of all, I want to talk about polar Protic solvents and what those compounds are. The most typical examples of our polar Protic solvents are going to be water, various solvents, like for instance methanol and ethanol that I have over here on the screen, and also we are going to see various aqueous solutions of inorganic acids or even solutions of carboxylic acids, which can be either neat, which means that it's a pure carboxylic acid like glacial acetic acid, which is pretty much a 98% carboxylic acid, acetic acid by itself, or it can be aqueous solution of carboxylic acids, or maybe even alcoholic solutions of carboxylic acids. The common feature of all polar Protic solvents is that they're going to have either H+, they can dissociate into the solution, and that's where our inorganic and carboxylic acids excel, or alternatively, our solvents can have a hydrogen, which is going to be extremely polarized due to its bond to electronegative element like oxygen or maybe nitrogen, something of that sort. So all these solvents, they have the same important feature, H+ or H delta plus, that is present. So typically, we are going to be looking either for molecules that are strong inorganic acids, or essentially for anything that is going to contain an OH group on its own as our source of Protic conditions, and we are going to consider those as our Protic solvents. Also, due to the fact that our Protic solvents are going to either provide H with a delta plus or a full plus in the case of the dissociating strong inorganic acids, they're always going to be polar solvents. It is impossible to have a Protic solvent that is not going to be polar at the same time. Protic solvents, they're always polar. Now, where do we normally see polar Protic solvents? When it comes to the substitution and elimination reactions, typically polar protic solvents are going to be associated with unimolecular reactions. So that means that they are going to be most typically our solvents in SN1 and E1 reactions. Can the SN1 and E1 reaction happen in other solvents? Yeah, sometimes. But why do we prefer polar protic solvent for the SN1 and E1 reaction? Well, the thing is, if we think about either of those unimolecular reactions and we think about how the reaction proceeds, we are going to have some sort of alkyl and we have our leaving group. I'm going to abbreviate that leaving group as an X of some sort. So that leaving group, when it dissociates, it typically going to give us a carbocation. I will show that as an R+, and we're also going to have X-, or potentially we can have another leaving group, but X- is going to be the most common one. So what polar protic solvent is going to do, it's going to surround our X- and prevent the back attack onto the carbocation. So essentially what polar protic solvent is going to do, it will facilitate the formation of the carbocation and it will pull that X- away from your molecule. So if let's say my polar protic solvent in this case is water, it's going to surround my X-, sort of make a fur coat of the solvent, the solvation shell around that X-, and it will prevent that X- from reattacking our carbocation, and at the same time it will stabilize it as well. So while in theory unimolecular reactions could proceed without the presence of the protic solvent, they're going to be quite rare because the polar protic solvent is quite literally necessary there to form the carbocation, and it is necessary to stabilize your leaving group. Otherwise, there is just no good reason for your leaving group to dissociate in the first place, and even if it were to dissociate, it would immediately reattack the carbocation and never go away in any appreciable distance so that the nucleophile can potentially come in and do any kind of reaction. So in reactions like that, we are always going to have polar protic conditions, polar protic solvent, simply because that solvent is required for the carbocation formation. Without that, there will be no carbocation. Now, when it comes to polar aprotic solvents, well, those compounds have one big similarity. They do not have any kind of OH groups on them. But other than that, they unfortunately do not have many other similarities outside of the fact that they are polar. So when it comes to your polar aprotic solvent, you pretty much will have to recognize it for every different reaction, and probably the best way to recognize polar aprotic solvents in your reactions is to, well, quite literally memorize the list. Luckily, the list is not very extensive. Among the most common polar aprotic solvents that you are going to see within the scope of your course, going to be DCM, which stands for dichloromethane, acetone, THF, or tetrahydrofurane, 1,4-dioxane, or sometimes we refer to that as just simply dioxane, acetonitrile, dimethyl sulfoxide, or also known as DMSO, and finally dimethylformamide, also known as DMF. This list is by far not exhaustive, however these are the most common solvents that you are likely to see in your course, and of course pay attention to what exactly your instructor likes to use, because different instructors have different favorite solvents, and maybe your instructor likes to use something else. Sometimes we are going to see people use things like HMPA and some other solvents, but as I said, look at what your instructor likes to use, look at your textbook, and make a list of the common solvents that you are going to see in your class, and as I said, most likely you're going to see all of these guys as well, in addition to whatever your instructor might like the most. Now, when do we normally use polar aprotic solvents? Well, when it comes to these guys, we commonly see those in the case of bimolecular reactions, and most commonly that's going to be SN2 reactions. And the big deal with polar aprotic solvents is that these guys are very good at solvating cations, which exposes the nucleophile in your reaction. Let me explain what I mean by that. Let's say we have potassium cyanide, so I have potassium that is positively charged, and I have cyanide which is going to be negatively charged. If this compound is not dissolved in the solvent, then potassium and cyanide make a very tight ionic pair. There is no reason for them to separate from each other, they are attracted from the electrostatic perspective, and they will also stabilize each other by, well, attracting to each other. Well, what polar aprotic solvent is going to do, it will separate those ions. So if I take my potassium cyanide and I use, let's say, acetonitrile as a solvent, then it's going to come in and start breaking those ions away from each other. So just like in the case with polar protic solvents when we surrounded our anionic species with this solvent, in this case we're kind of doing the same thing but for the cation. Here we're going to surround our cation with those solvent molecules, pulling it away from the anion, so that means that my cyanide that I had to begin with is now completely naked and it doesn't have any counter ion with it, which means that now it is going to be actively pursuing any kind of reaction that it can in order to stabilize itself, in order to give that excess of electron density towards something, and that makes it now into a very aggressive nucleophile. So by using polar aprotic solvent in our SN2 reaction, we increase the nucleophilicity of our compounds and we facilitate reaction by making our nucleophile, like I like to joke, naked and aggressive. So in this case, without the polar aprotic solvent, SN2 reaction is still possible, but it's going to be rather problematic because our cation will be sticking to our anionic nucleophile and reaction is not going to be proceeding very readily. But as soon as we pull those guys away from each other, as soon as we have our cation surrounded by the solvent and our anionic nucleophile minding its own business and not particularly happy with being negative, then the reaction is going to proceed quite easily. So now you know what's the point in having polar protic solvents in SN1 and E1 reactions and why we require polar aprotic solvents in the SN2 reactions. If you learned something new today, please give this video a like to help it promote and help more students see this video, subscribe to the channel for daily organic chemistry updates, watch this video next, and I will see you tomorrow.